Mars will be humanity's grave, not because we'll die there, but because it's where our cosmic ambitions will finally hit an immovable wall. The outer solar system? Forget it. Other star systems? Fantasy. Everything beyond that pale red dot might as well be in another universe. And here is a question. If you were the first human to set foot on Mars, what's the very first thing you'd do? Comment down below. I will pin the most creative answer. Now let's begin. When we say Mars is far away, we're not just talking about a long road trip. We're talking about a gulf so vast that it fundamentally changes everything about how humans can survive the journey. At its closest approach to Earth, Mars is still 54,600,000 kilometers away. At its farthest, 400 million kilometers. That's not just a number on a page. That's a distance so immense that light itself, traveling at nearly 300,000 kilometers per second, takes between 4 and 24 minutes to cross it. Imagine trying to have a conversation with someone where every question takes up to 24 minutes to reach them, and their answer takes another 24 minutes to get back to you. That's 48 minutes for a single exchange. Now imagine you're in danger. You need help. You send an emergency signal to Earth and you sit there, knowing that even if someone responds instantly, you won't hear back for nearly an hour. You're truly alone in a way that no human explorer has ever been alone before. The astronauts on the International Space Station are just 400 kilometers above Earth. If something goes wrong, they can be home in hours. The Apollo astronauts who went to the Moon were 384,000 kilometers from home. Far, yes, but still within a realm where Earth could help them. When Apollo 13 suffered that catastrophic explosion, Mission Control worked with the crew in real time to bring them home. There was fear, there was danger, but there was also immediate communication and support. Mars is different. Mars is lonely in a way we've never experienced. A typical round-trip mission to Mars would last around 850 days. That's more than 2 years. 2 years where you cannot simply turn around and come home if something goes wrong. The orbital mechanics that govern planetary motion don't care about emergencies. Earth and Mars align favorably for travel only once every 26 months. Miss your window and you're stuck waiting for the next one. During those 2 years, you'll spend roughly 500 to 700 days in transit, cooped up in a spacecraft smaller than most apartments, breathing recycled air, eating preserved food, and watching Earth become a tiny blue dot, then disappear entirely into the cosmic background. If this kind of deep dive into space exploration fascinates you, please hit that subscribe button and give this video a thumbs up. Your support helps me continue exploring them with you. But distance is just the beginning of our problems. The real challenge waiting for any crew attempting to reach Mars is something invisible, something silent, and something absolutely deadly: radiation. Out here on Earth, we live beneath a protective shield we rarely think about. Our planet's magnetic field, generated by the churning iron core deep beneath our feet, extends thousands of kilometers into space, deflecting charged particles from the Sun. Our atmosphere, that thin blanket of nitrogen and oxygen we breathe, absorbs cosmic rays and solar radiation before they can reach us. We are protected. We are safe. We don't realize how rare that is. Mars has no global magnetic field. It lost that protection billions of years ago when its core cooled and solidified. Its atmosphere is less than 1% as thick as Earth's. Standing on the surface of Mars is like standing on a mountaintop during a radiation storm, except the storm never ends. The radiation that bombards Mars comes from 2 primary sources. First, there's solar radiation, energetic particles ejected from the Sun during solar flares and coronal mass ejections. These events are unpredictable and can unleash doses of radiation lethal to unprotected humans within hours. Then there's galactic cosmic radiation, or GCR. These are particles accelerated to nearly the speed of light by supernova explosions, black holes, and other violent cosmic events scattered across the galaxy. They've been traveling through space for millions of years, and they don't stop for anything. They pass through spacecraft hulls, through spacesuits, through human bodies, slicing through DNA and damaging cells at the molecular level. NASA's Radiation Assessment Detector, which has been measuring radiation levels on Mars since the Curiosity rover landed in 2012, has given us sobering data. An astronaut spending just 1 year on the Martian surface would receive a radiation dose equivalent to roughly 250 millisieverts. To put that in perspective, the annual radiation limit for nuclear power plant workers here on Earth is 50 millisieverts. A single chest X-ray gives you about 0.1 millisieverts. 250 millisieverts might not sound catastrophic at first. It's not immediately lethal, but here's what makes it terrifying. That's just the surface dose. The journey to Mars adds another dose, the journey back adds another. By the time an astronaut completes a typical Mars mission, they could accumulate between 600 and 900 millisieverts of radiation exposure, and that's assuming no major solar events occur during the trip. NASA's current career limits for astronauts are set at levels designed to keep their lifetime risk of developing fatal cancer below 3%. A single Mars mission could push an astronaut right up against, or even beyond, that limit. You go to Mars once, and your career as an astronaut is essentially over. You can never go back to space again because the radiation risk becomes unacceptable. But cancer risk isn't even the worst part. Recent studies have revealed something more immediately concerning. Cosmic radiation damages the central nervous system. Experiments with mice exposed to simulated galactic cosmic rays showed impaired memory, reduced cognitive function, increased anxiety, and damaged neurons. The mice, in essence, lost their ability to think clearly. Now imagine being on Mars, millions of kilometers from home, in a life or death situation requiring split-second decisions, and your brain isn't working properly because cosmic rays have been steadily degrading your neural tissue for months. That's not just a health risk, that's a mission failure waiting to happen. Scientists have proposed shielding solutions, of course. Lead shielding, water walls, polyethylene barriers, even using Martian regolith, the dusty soil covering the planet's surface, to build protective habitats. But here's the problem: mass. Every kilogram you want to launch to Mars costs thousands of dollars and requires fuel. Building adequately shielded habitats would require transporting massive amounts of material, making missions exponentially more expensive and complex. And even if we solve the shielding problem for habitats, astronauts would still need to venture outside. They'd need to conduct experiments, repair equipment, explore the terrain. Every moment spent outside the shielded habitat is another moment of exposure. Some researchers have suggested we simply accept the risk. After all, early explorers on Earth faced tremendous dangers. Many died, but they pushed forward anyway because the human spirit demands exploration. That argument has merit, but there's a crucial difference. Those early explorers knew the risks they faced: storms, disease, hostile environments, yes, but risks that were at least somewhat predictable and manageable. Cosmic radiation is different. It's invisible, unavoidable, and accumulates silently until the damage is done. So radiation is one wall we're crashing into. But there's another challenge that makes Mars uniquely difficult, something that affects every single aspect of mission planning: gravity, or rather the lack of it. Speaking of the harsh realities of Mars, I recently made a video called "Mars Colonization is More Terrifying Than You Think," that explores some of these challenges in even greater detail. If you want to understand just how hostile the red planet really is, check it out after this one. The link is in the description below. Mars has about 38% of Earth's gravity. That might sound like enough to keep astronauts healthy, but here's the problem. We don't actually know if it is. We have extensive data on microgravity from decades of space station research. We have data on Earth's gravity because, well, we live here, but we have zero long-term data on partial gravity environments. The human body is a finely tuned machine adapted to one specific gravitational environment, Earth's. Remove that gravity, as we've seen with astronauts on the International Space Station, and the body starts to deteriorate. Bones lose density at a rate of 1 to 2% per month. Muscles atrophy. The cardiovascular system weakens because the heart doesn't have to work as hard to pump blood. Fluids shift upward, causing vision problems as pressure builds behind the eyes. The immune system becomes compromised. These effects are well documented in microgravity. What we don't know is whether Mars's partial gravity is enough to prevent these problems, or whether it merely slows them down. Would an astronaut spending 18 months on Mars return with bones so weak they'd fracture under Earth's gravity? Would their hearts be unable to pump blood effectively once they got home? There's only one way to find out. Send people to Mars and see what happens. That's not a scientific experiment. That's a gamble with human lives. Then there's the psychological dimension. 2 years in an isolated, confined environment with the same small group of people, knowing that any mistake could kill you, knowing that Earth is too far away to help, knowing that you're breathing recycled air and drinking recycled water and eating food that's been sitting in storage for months. The psychological strain would be immense. NASA has conducted isolation experiments like the HIC's missions in Hawaii, where crews lived in Mars-like habitats for up to a year. Even in these controlled environments on Earth, with the knowledge that they could leave if necessary, participants experienced significant stress, interpersonal conflicts, and mental fatigue. Now multiply that by the actual danger of being on Mars. The constant awareness that a single equipment failure, a single breach in your habitat, could mean death. The loneliness of looking up at the night sky and not seeing Earth. The weight of knowing that if something goes catastrophically wrong, you will die on an alien world, and your body will never return home. Some people might be psychologically resilient enough to handle that. But how do you test for that? How do you know, before sending someone on a 2-year mission to Mars, that they won't break under the pressure? And what happens if they do break? What happens if your mission commander, the person everyone depends on, has a psychological crisis in the middle of the mission? These aren't hypothetical questions. These are real challenges that mission planners are wrestling with right now. And we haven't even talked about the technical challenges yet. Life support systems that must function flawlessly for years. Power systems that can survive dust storms blocking out the sun for weeks at a time. Communication systems that must work despite the 48-minute delay. Medical equipment capable of handling everything from minor injuries to major emergencies because there's no hospital on Mars, no emergency room, no surgeon standing by. Every single system must be redundant, reliable, and repairable with limited resources. Because here's the brutal truth, if something breaks on Mars, you can't order a replacement part. You can't call for backup. You have to fix it yourself with whatever materials and tools you brought with you, or you die. The Mars rovers we've sent have taught us some hard lessons about equipment reliability. Spirit got stuck in soft soil and eventually died when it couldn't angle its solar panels toward the sun. Opportunity was lost during a massive dust storm that blocked sunlight for months, draining its batteries. These were robots, machines we could afford to lose. When it's human lives at stake, the margin for error disappears entirely. Let's talk about dust for a moment, because Martian dust is not like Earth dust. It's fine, almost like powder, and it gets everywhere. It's electrostatically charged, meaning it clings to surfaces and is incredibly difficult to remove. It's also abrasive and potentially toxic, containing perchlorates, chemical compounds that are harmful to human health. During the dust storms that periodically engulf Mars, visibility drops to near zero. Solar panels become useless, equipment gets coated, seals and joints get contaminated. Imagine trying to maintain complex life support systems when every time you open a hatch, toxic dust billows into your habitat. Imagine trying to keep your spacesuits functional when the dust is grinding away at the joints and seals with every movement. The Apollo astronauts dealt with lunar dust, and they reported that it was one of the most annoying and persistent problems they faced. Lunar dust is sharp and jagged because there's no wind or water to smooth it. Martian dust has been weathered by ancient winds, so it's smoother, but there's vastly more of it, and it moves in ways lunar dust never did. So we have radiation that's slowly killing you, we have gravity that might be destroying your bones and muscles, we have psychological stress that could break your mind, we have equipment that must never fail, and we have an environment so hostile that simply existing there requires constant vigilance and effort. And all of this assumes we can even get there safely. The journey to Mars takes between 6 and 9 months, depending on the trajectory chosen. That's 6 to 9 months in a spacecraft exposed to cosmic radiation, living in microgravity with limited space and resources. The spacecraft becomes your entire world. There's nowhere to go, nothing to see except the blackness of space and the distant points of stars. During the Artemis 1 mission in 2022, NASA tested radiation exposure on a lunar trajectory. Even that relatively short trip provided valuable data, validating models that predicted radiation doses between Earth and Mars. The measurements confirmed what scientists feared. The radiation environment in deep space is brutal. Crews would be exposed to continuous bombardment from galactic cosmic rays, with no planetary magnetic field to protect them. Some mission designs propose faster transit times using more powerful propulsion systems. Nuclear thermal propulsion, for instance, could potentially cut the travel time to Mars in half. But nuclear rockets bring their own challenges: development costs, safety concerns, political hurdles, and the sheer technical difficulty of building and testing systems that have never flown before. Even with faster transit, you're still looking at months in space, months where your body is deteriorating, months where your psychological reserves are being drained, months where a single critical failure means death because there's no rescue coming, no safe harbor nearby. And then there's the landing itself. Landing on Mars is terrifyingly difficult. The atmosphere is thick enough to create tremendous heat during entry, requiring heat shields and careful trajectory planning, but too thin to provide much help with deceleration. You're coming in at thousands of kilometers per hour, and you need to slow down to a safe landing speed using a combination of heat shields, parachutes, and retro rockets. NASA has successfully landed multiple rovers on Mars, each one a triumph of engineering. But rovers weigh 1 or 2 tons at most. A human mission would require landing something weighing 40 to 50 tons, possibly more when you factor in habitats, supplies, and equipment. That's an entirely different scale of challenge. The entry, descent, and landing sequence, often called 7 minutes of terror because of the time it takes and the fact that it all happens autonomously due to the communication delay, becomes even more terrifying when human lives are inside the spacecraft. Every calculation must be perfect. Every system must function flawlessly. There's no margin for error, no second chances. And once you're on the surface, you need a way to get back off. Mars has about 38% of Earth's gravity, which means launching from the surface requires substantial fuel and a rocket powerful enough to achieve escape velocity. That rocket either needs to be sent ahead of the crew and sit waiting on the surface, exposed to the Martian environment for months or years, or it needs to be brought with the crew, adding even more mass to the initial landing. Some mission architectures propose manufacturing fuel on Mars using local resources, a process called in situ resource utilization. The idea is elegant. Use the carbon dioxide in Mars's atmosphere and water extracted from ice deposits to create methane and oxygen, the propellants needed for the return journey. But this requires sending chemical processing plants to Mars, setting them up, and ensuring they work reliably for months or years before the crew even arrives. It's theoretically possible. NASA's Perseverance rover even demonstrated a small-scale version of this technology with the MOXIE experiment, which successfully produced oxygen from Martian atmosphere. But scaling that up to produce enough fuel for a human mission is another matter entirely. It's the difference between lighting a candle and running a power plant. Every solution we propose for getting to Mars, landing on Mars, surviving on Mars, and returning from Mars adds layers of complexity, cost, and risk. And the more complex a system becomes, the more points of potential failure exist. This is why some scientists and engineers are starting to say that Mars might represent a hard limit on human exploration. Not because we lack the technology in principle, but because the accumulated challenges might simply be too great to overcome safely and sustainably. Think about it this way. Earth to the Moon is a difficult journey, but it's within reach. We did it in the 1960s with computers less powerful than modern smartphones. Earth to Mars is exponentially harder. Every problem we face going to the Moon is magnified tenfold or more for Mars. So what about going beyond Mars? What about the outer solar system, the moons of Jupiter and Saturn, the distant ice worlds at the edge of our solar system? If Mars is this difficult, those destinations become nearly impossible for human exploration with anything resembling current technology. Jupiter's moon Europa, with its subsurface ocean that might harbor life, sits 628 million kilometers from the Sun at its closest. That's nearly twice the distance to Mars. Saturn's moon, Enceladus, another candidate for extraterrestrial life, is 1.2 billion kilometers away. These aren't just numbers. These are distances that represent years of travel time, decades of mission planning, and levels of radiation exposure that would be unsurvivable without revolutionary breakthroughs in shielding technology. And that's just within our own solar system. The nearest star to our Sun, Proxima Centauri, sits 4.2 light-years away. That means light, the fastest thing in the universe, takes 4.2 years to travel that distance. With our current propulsion technology, a spacecraft would take tens of thousands of years to reach it. Even with theoretical advanced propulsion systems that might achieve a significant fraction of light speed, we're still talking about journeys lasting decades or centuries. The universe, it seems, is fundamentally hostile to the idea of humans spreading across it. The distances are too vast, the environment's too deadly, the energy requirements too enormous. We are creatures evolved for one specific planet with one specific gravity, one specific atmosphere, one specific magnetic field. Venturing beyond that protective bubble pushes us to our absolute limits. But let's return to Mars, because Mars is where the boundary becomes clearest. Mars is where we can almost touch the dream of becoming a multiplanetary species, but where reality imposes harsh constraints we cannot ignore. One of the most sobering aspects of Mars mission planning is something called the conjunction class versus opposition class debate. These are two fundamentally different approaches to getting humans to Mars and back, and each reveals something important about our limitations. A conjunction class mission takes advantage of the most fuel-efficient trajectories. The crew would spend roughly 500 days on the Mars surface, waiting for the planets to align favorably for the return journey. Total mission time, around 900 days, or about 2.5 years. This approach minimizes fuel requirements and allows for meaningful exploration time on Mars, but it subjects the crew to maximum radiation exposure and psychological stress. An opposition class mission, by contrast, minimizes time away from Earth. The crew might spend only 30 to 60 days on Mars before launching for the return journey, bringing the total mission time down to around 500 days. This reduces radiation exposure and psychological strain, but it requires much more fuel because you're not using optimal transfer windows. It also means you travel all that way for barely a month on the surface. Imagine spending 6 months getting to Mars, 30 days exploring, and 6 months coming home. It hardly seems worth the risk and cost. Both options are compromises and both reveal a fundamental truth. There is no good way to send humans to Mars with current technology. Every approach involves accepting significant risks and limitations. NASA's current plan, as outlined in their Moon to Mars architecture, acknowledges these challenges. The strategy involves first establishing a sustainable presence on the Moon through the Artemis program, using our nearest neighbor as a testing ground for technologies and procedures that would be needed for Mars. The Moon is close enough that we can iterate, learn from mistakes, and develop confidence in our systems before committing to the far more dangerous journey to Mars. This is wise planning, but it also reveals an uncomfortable reality. If we need this much preparation and testing just to attempt Mars, what does that say about going further? If Mars requires decades of development and billions of dollars in investment, and even then carries substantial risk of mission failure or crew loss, how can we possibly justify attempting missions to the outer solar system? Let me paint a picture of what a realistic Mars mission might look like, based on current planning and our understanding of the challenges involved. First, we send cargo missions, multiple heavy-lift rockets carrying habitats, supplies, fuel production equipment, rovers, power systems, and emergency backup systems. These are launched during optimal windows, taking months to reach Mars, and they land autonomously at a pre-selected site that offers the best combination of scientific interest, resource availability, and landing safety. For the next year or two, robotic systems set up the infrastructure, solar panels are deployed, or nuclear reactors are activated to provide power. Fuel production plants begin extracting carbon dioxide from the atmosphere and water from subsurface ice, slowly manufacturing the propellants needed for the return journey. Habitats are inflated and tested, supply caches are verified, communication relays are established. Only after all of this is confirmed to be working do we launch the crew. 4 to 6 astronauts carefully selected for their technical skills, psychological resilience, and ability to work as a team under extreme stress. They launch during the next favorable window, spending 6 to 9 months in a spacecraft that will be their home, their workplace, and their prison. They arrive at Mars and face the terrifying descent to the surface. If anything goes wrong during those 7 minutes, they die. There's no abort option, no second chance. But let's assume everything works perfectly. They land safely and make their way to the pre-positioned habitat. Now they're on Mars. For the next 500 days, give or take, this is their life. Wake up in a habitat the size of a small house. Perform system checks to make sure life support is functioning. Eat breakfast from pre-packaged meals that all taste vaguely the same. Suit up for the day's activities, a process that takes hours because Martian spacesuits are complex pieces of equipment. Venture outside into a landscape of rust-colored rock and dust under a butterscotch sky. The temperature is perhaps minus 60 degrees Celsius, cold enough to freeze carbon dioxide into dry ice. The atmospheric pressure is less than 1% of Earth's, meaning that without a pressurized suit, your blood would literally boil. Conduct experiments, collect samples. Maintain equipment, return to the habitat before the thin atmosphere makes the temperature plummet even further at night. Remove the suit, clean away as much dust as possible, knowing you'll never get it all. Eat dinner, communicate with Earth, knowing that your messages won't be answered for at least 48 minutes. Try to sleep while cosmic rays pass through your body, through the habitat walls, unstoppable and invisible. Repeat this for 500 days, day after day after day. with the same people in the same confined space, knowing that the tiniest mistake, the smallest equipment failure, could cascade into disaster. And during all of this, your body is changing. Your bones are losing density, your muscles are weakening despite exercise regimens, your brain is being damaged by radiation, your psychological reserves are being drained by the isolation and stress. Finally, the launch window opens. You climb into the ascent vehicle, a rocket that's been sitting on the Martian surface for months or years, exposed to temperature swings, dust storms, and radiation. You ignite the engines and pray that everything works, because if it doesn't, you're stranded on Mars forever. There is no rescue mission. Earth is too far away, and launching another mission would take years, but again, let's assume success. You achieve orbit and rendezvous with the return vehicle, either one you brought with you or one that was sent ahead. Now you face another 6 to 9 months in space, your body already weakened, your psychological state already fragile. You watch Mars recede behind you, wondering if you'll even survive long enough to see Earth again. Months pass, the crew compartment feels smaller every day, tempers fray, sleep becomes difficult. You exercise obsessively, trying to maintain muscle mass and bone density for the crushing gravity that awaits you back home. You monitor your radiation exposure and watch the numbers climb higher and higher, knowing that you're pushing against safe limits, possibly beyond them. Earth finally appears in your window, that beautiful blue marble growing larger day by day. Relief floods through you, but the mission isn't over yet. You still have to survive re-entry, a violent plunge through Earth's atmosphere at speeds that generate temperatures hot enough to melt metal. The heat shield holds, the parachutes deploy, you splash down in the ocean or touch down on solid ground. Rescue teams rush to extract you from the capsule because after 2.5 years, in reduced gravity, you cannot walk. Your legs cannot support your weight, your heart struggles to pump blood against Earth's gravity. You're lifted onto stretchers and carried away, beginning months of rehabilitation to regain the strength your body lost. Medical teams examine you thoroughly. They find decreased bone density, muscle atrophy, cardiovascular deconditioning, vision problems from fluid shifts, and cognitive changes from radiation exposure. You're alive, but you're not the same person who left Earth 2.5 years ago, and the long-term effects won't be known for years, possibly decades. What's your cancer risk now? Will you develop early-onset dementia from the neural damage? Will your children inherit genetic mutations caused by cosmic ray impacts to your DNA? This is the reality of a Mars mission. Not the inspiring videos and dramatic music of NASA promotional materials, but the grinding, exhausting, dangerous reality of human beings trying to survive in an environment that wants to kill them. And this is just one mission, one crew, one round trip. The word colonization gets thrown around casually when people talk about Mars, but colonization implies permanence, sustainability, growth. It implies families, children being born, communities developing, a self-sufficient civilization emerging. Can you imagine raising a child on Mars, a child who grows up in 1/3 of Earth's gravity, whose bones and muscles develop in that environment? What happens if that child ever comes to Earth? Would their body, adapted to Martian gravity, be crushed by Earth's pull? Would they be permanently trapped on Mars, unable to ever visit the planet of their ancestors? And what about the medical care a pregnant woman would need? The resources required to support a newborn? The psychological impact of raising children in an enclosed habitat, never feeling wind on their face, never swimming in an ocean, never running through a forest? These aren't trivial questions. These are fundamental challenges to the very concept of colonization. Some futurists propose terraforming Mars, transforming it over centuries or millennia into an Earth-like world with a thicker atmosphere, warmer temperatures, and maybe even liquid water on the surface. The idea is romantic and appears in countless science fiction stories, but the reality is staggeringly difficult. Mars lost its atmosphere because it lost its magnetic field. Without that protective shield, the solar wind, a constant stream of charged particles from the Sun, gradually stripped away the Martian atmosphere over billions of years. This process is still happening today, just at a slower rate because there's less atmosphere left to strip away. To terraform Mars, you'd need to somehow thicken the atmosphere substantially. Proposals include releasing greenhouse gases from subsurface deposits, bombarding the polar ice caps with nuclear weapons to release frozen carbon dioxide, or even redirecting comets to crash into Mars, delivering water and volatile compounds. All of these ideas require technology we don't possess, energy expenditures that are almost incomprehensible, and timescales measured in centuries at minimum. And even if you somehow thickened the atmosphere, the solar wind would just strip it away again unless you could somehow restart Mars's magnetic field. That would require remelting the planet's core, a feat so far beyond our capabilities that it ventures into the realm of fantasy rather than engineering. So permanent colonization in the sense of creating a truly Earth-like Mars is almost certainly impossible with any technology we can currently envision. What we're really talking about when we discuss Mars colonies is enclosed habitats, underground bunkers, and domed settlements. Humans living permanently in artificial environments, completely dependent on technology for survival, one equipment failure away from catastrophe. Is that sustainable? Can a community survive long-term in such conditions? Human history suggests we're remarkably adaptable, but we've never attempted anything quite like this. We have people living in Antarctica for extended periods, but they can leave. They know there's a world beyond the ice. Mars colonists would have no such escape. Mars would be their entire reality, potentially forever. The psychological implications are profound. Humans evolved in rich, diverse environments with access to nature, varied landscapes, changing seasons, and complex ecosystems. What happens to human psychology when all of that is stripped away, when your entire world is artificial corridors, recycled air, and the same few faces day after day? Some research suggests that access to nature is fundamental to human mental health. Studies show that people living in urban environments without green spaces experience higher rates of depression, anxiety, and other mental health issues. Astronauts on the International Space Station report that one of the things they miss most is nature: trees, grass, the sound of wind, the smell of rain. On Mars, there is no nature. There's only rock, dust, and the thin, poisonous atmosphere. You might have hydroponics gardens inside the habitat, small patches of green providing fresh food and psychological comfort, but it's not the same as a forest or a meadow. It's a pale imitation, a reminder of what you've lost. And yet, despite all of these challenges, despite the radiation and the distance and the psychological strain and the technical complexity and the enormous cost, we're probably going to try anyway. Because that's what humans do. We push boundaries, we explore, we take risks in pursuit of knowledge and achievement. The question isn't whether we can send humans to Mars. We probably can, given enough time, money, and willingness to accept risk. The question is whether we should and whether we can go beyond Mars. Let's consider the alternatives. Instead of risking human lives, we could send increasingly sophisticated robots. The rovers we've already sent to Mars, Spirit, Opportunity, Curiosity, and Perseverance, have revolutionized our understanding of the red planet. They've found evidence of ancient water, analyzed soil composition, studied the atmosphere, and even recorded the sound of Martian wind. Future robots could be even more capable. Advances in artificial intelligence could create autonomous systems that make decisions without waiting for instructions from Earth. Advances in robotics could create machines that can drill deeper, travel farther, and analyze samples with greater precision than current technology allows. Sample return missions, robots that collect Martian material and bring it back to Earth, could allow scientists to study Mars rocks and soil with laboratory equipment far more sophisticated than anything we could send to the planet's surface. No human risk, lower cost, and potentially greater scientific return. But here's the counter-argument: robots can't adapt like humans can. They can't make intuitive leaps, recognize patterns that weren't programmed into their systems, or respond creatively to unexpected discoveries. A human geologist on Mars could examine a rock outcrop and immediately recognize features that would take a rover months to analyze. Humans can go places robots can't, work faster, and make decisions in real time. There's also something fundamentally important about human presence that transcends pure scientific or economic calculation. When Neil Armstrong stepped onto the moon in 1969, it wasn't just a scientific achievement, it was a defining moment in human history, a declaration that we are not bound to one world, that we can reach beyond our planetary cradle. The cultural and inspirational impact of that moment cannot be quantified, but is nonetheless real and significant. A human mission to Mars would have similar impact. It would inspire a generation of scientists, engineers, and explorers. It would demonstrate that despite our problems here on Earth, despite our conflicts and divisions, we can still accomplish extraordinary things when we work together toward a common goal. But inspiration has to be weighed against risk and cost. Is sending humans to Mars worth the potential loss of life? Is it worth the hundreds of billions of dollars it would require? Money that could be spent on other priorities? These are questions each society has to answer for itself. And the answers will vary depending on values, priorities, and circumstances. What seems increasingly clear, however, is that even if we do send humans to Mars, even if we establish some kind of permanent presence there, Mars likely represents the outer boundary of direct human exploration for the foreseeable future, possibly forever. The solar system beyond Mars becomes exponentially more hostile. Jupiter, the gas giant that dominates the outer solar system, sits in a radiation environment so intense that it would kill an unshielded human in hours, possibly minutes. The planet's powerful magnetic field traps charged particles, creating radiation belts far more dangerous than Earth's Van Allen belts. Jupiter's moon Europa, despite being one of the most tantalizing targets in the search for extraterrestrial life, sits right in the heart of this radiation hell. NASA's Europa Clipper mission, launched in October of 2024, will study the moon using a series of flybys, dipping into the radiation zone briefly before retreating to safer distances. Even this robotic spacecraft, specifically hardened against radiation, can only withstand limited exposure. A human mission to Europa is virtually inconceivable with current technology. The radiation would require shielding so massive that launching it would be prohibitively expensive. The distance would mean a journey of several years, even with optimal trajectories. And for what? To orbit a moon we could study far more safely and cheaply with robots. Saturn, Uranus, and Neptune present similar challenges, with the added difficulty of even greater distances. The Voyager 2 spacecraft, launched in 1977, took 12 years to reach Neptune. Imagine keeping a human crew alive and sane for 12 years in a spacecraft. Imagine the life support requirements, the food and water, the spare parts and backup systems. The spacecraft would need to be enormous, and launching something that large would require propulsion technology we simply don't have. This is why Mars might truly be the boundary. Not because there's some magical line drawn in space, but because the accumulated practical difficulties of going further become insurmountable, at least with anything resembling our current understanding of physics and engineering. Some people point to breakthrough propulsion concepts as potential game changers. Nuclear pulse propulsion, where you literally detonate nuclear bombs behind your spacecraft to push it forward. Antimatter rockets using the most energy-dense fuel theoretically possible. Light sails pushed by powerful lasers, warp drives that somehow manipulate space-time itself. These ideas range from theoretically possible but enormously difficult to completely speculative physics that might not even be achievable in principle, and even the most optimistic projections for these technologies place them decades or centuries in the future, if they're possible at all. Nuclear pulse propulsion, also known as Project Orion, was studied seriously in the 1950s and 60s. The physics works: you could build a spacecraft that rides a series of nuclear explosions. But the engineering challenges are immense, the political and environmental concerns are staggering, and even with this technology, you're still talking about multi-year journeys to the outer solar system. Antimatter sounds like science fiction, and functionally, it is. We can create tiny amounts of antimatter in particle accelerators, but it takes enormous amounts of energy to produce even microscopic quantities. The entire annual production of antimatter by all the accelerators on Earth wouldn't be enough to power a light bulb for more than a few minutes. Scaling that up to produce enough antimatter to fuel a spacecraft is a problem so far beyond our current capabilities that it's not even meaningful to discuss timelines. Light sails, thin reflective surfaces pushed by photon pressure from the sun or from laser arrays, are more realistic. Organizations like the Breakthrough Starshot Initiative propose using powerful ground-based lasers to accelerate small probes to a significant fraction of light speed, potentially reaching nearby stars within decades rather than millennia. But these would be tiny probes, measuring just a few grams, carrying minimal instrumentation. There's no conceivable way to scale this technology to accelerate anything large enough to carry humans. The energy requirements would be astronomical, and the engineering challenges of keeping a laser focused on a spacecraft traveling at relativistic speeds across interstellar distances would be nightmarish. Warp drives, the staple of science fiction, remain firmly in the realm of speculation. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical solution to Einstein's field equations that would allow faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. But this requires exotic matter with negative energy density, something we've never observed and aren't sure even exists. And even if it does exist, the energy requirements calculated for an Alcubierre drive are absurd, potentially requiring the mass energy equivalent of entire planets, or even stars. So when we look at the practical reality, when we set aside the speculation and focus on what we can actually do with technology that exists or could realistically be developed in the coming decades, Mars really does appear to be the limit. This is simultaneously humbling and profound. We live in a vast universe containing billions of galaxies, each with billions of stars, many of those stars with planets orbiting them. The cosmos is unimaginably large, filled with wonders we can barely glimpse through our telescopes, and yet we might be confined to this one tiny corner of it, able to send our robotic emissaries across the solar system and beyond, but unable to follow them ourselves. There's something deeply moving about this realization. We are the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own existence and origins. We are made of atoms forged in the cores of ancient stars, scattered across space when those stars died, reassembled on this one planet into forms capable of looking back up at the stars and wondering. And yet, for all our consciousness, for all our intelligence and creativity and ambition, we remain bound by the laws of physics that govern the universe. We can understand those laws, we can work within them, we can accomplish remarkable things, but we cannot break them. The universe is not designed for our convenience. It simply is, indifferent to our desires and dreams. This doesn't mean we should stop exploring. It doesn't mean we should abandon the dream of reaching Mars or searching for life in the oceans of Europa or studying the methane lakes of Saturn's moon Titan. It simply means we need to be realistic about what's possible and what isn't, about where we should invest our limited resources and what risks are worth taking. There's also a deeper question here about the purpose of human space exploration. Why do we want to go to Mars? Why do we dream of colonizing other worlds? What are we really seeking? For some, it's about survival. Earth faces existential risks, asteroid impacts, climate change, nuclear war, pandemics, artificial intelligence gone wrong. If humanity is confined to one planet, a single catastrophic event could end our species. Becoming multiplanetary would be insurance against extinction, ensuring that even if Earth is destroyed or becomes uninhabitable, human civilization continues elsewhere. This argument has intuitive appeal, but it requires examination. First, Mars is not a refuge from most of the threats we face. Climate change on Earth, even in the worst-case scenarios, would still leave our planet far more habitable than Mars is now or ever will be. Nuclear war would be devastating, but survivors would still have breathable air and drinkable water, things Mars doesn't offer. A pandemic that spreads across Earth might reach Mars too, carried by the very colonists we send. Asteroid impacts are the exception. A large enough impact could indeed make Earth uninhabitable while leaving Mars unaffected, but such impacts are rare on timescales relevant to human civilization. We're more likely to face existential risks from our own technology, and those risks would follow us to Mars. Second, a Mars colony would be completely dependent on Earth for decades, probably centuries. If something happened to Earth before Mars became self-sufficient, the Martian colony would die too. You can't maintain a technological civilization on Mars without sophisticated manufacturing, and you can't maintain sophisticated manufacturing without a large population and resource base, neither of which Mars would have in the early stages of colonization. So Mars as a backup for humanity only works if we're talking about very long time scales, multiple centuries of development, massive investment of resources, and successful navigation of all the technical and human challenges we've discussed. That's not impossible, but it's also not a near-term solution to existential risk. For others, space exploration is about resources. Asteroids contain vast amounts of valuable metals. The Moon has helium-3, a potential fuel for fusion reactors. Mars might have minerals and compounds worth harvesting. Perhaps expansion into space is driven by economics, by the promise of wealth beyond Earth. This argument also faces challenges. The cost of extracting and returning resources from space with current technology vastly exceeds their value. Yes, there are asteroids made primarily of iron and nickel, some containing platinum group metals worth trillions of dollars at current market prices. But launching the equipment to mine those asteroids, processing the materials in space, and returning them to Earth would cost more than the resources are worth. This could change with advances in technology or changes in market conditions. If certain rare elements become scarce on Earth, if launch costs decrease dramatically, if we develop in-space manufacturing that doesn't require returning materials to Earth, the economics might shift. Some companies are betting on this future, investing in asteroid mining technology and orbital manufacturing. But we're still in the very early stages, and it's unclear whether space resources will ever be economically competitive with terrestrial sources. For still others, the drive to explore space is about knowledge, about understanding our place in the universe, about answering fundamental questions. Are we alone? How did life begin? What is the nature of the cosmos? These are questions that have driven human inquiry for millennia, and space exploration is their natural extension. This motivation is perhaps the purest, least tainted by practical considerations or economic calculation. The search for knowledge is intrinsically valuable regardless of practical applications. Understanding the universe is part of what makes us human, part of how we find meaning in existence. And there are profound questions that can only be answered by exploring space. The question of whether life exists elsewhere is one of the most fundamental we can ask. If we find evidence of life on Mars, even extinct microbial life, it would revolutionize our understanding of biology and our place in the cosmos. If we find living organisms in the subsurface oceans of Europa or Enceladus, it would suggest that life arises wherever conditions permit, that the universe might be teeming with biology. But here's the critical point. We can pursue these questions, we can explore space and search for answers without necessarily sending humans. Robotic missions can collect samples, analyze chemistry, search for biosignatures, and transmit their findings back to Earth. They can go places too dangerous for humans, operate for years or decades without resupply, and cost a fraction of what human missions would require. The Mars rovers have been extraordinarily successful in their scientific missions. Curiosity has been operating on Mars since 2012, far exceeding its planned mission duration, making discoveries about Martian geology and past habitability. Perseverance, which landed in 2021, is actively searching for signs of ancient life and collecting samples for eventual return to Earth. These robots are not replacements for human explorers in every sense. They're slower, more limited in their capabilities, unable to make the intuitive leaps and creative decisions that humans excel at. But they're also immune to radiation, indifferent to isolation, unaffected by low gravity, and they don't need to come home. So perhaps the realistic vision for space exploration is a hybrid one. Humans pushed to Mars, establishing a presence on the surface, learning to live and work in that environment, demonstrating that we can survive beyond Earth. But beyond Mars, we rely increasingly on robotic emissaries, machines that explore on our behalf, extending our senses and our curiosity across the solar system and eventually into interstellar space. This isn't a failure of ambition. It's an acceptance of reality, a recognition that the universe imposes limits on what we can do, but that those limits don't prevent us from exploring and learning and growing as a species. The boundary at Mars, if it is indeed a boundary, is not a wall preventing all further progress. It's more like a transition point, a place where the nature of exploration changes from direct human presence to remote investigation. We can still study the outer solar system, still search for life on Europa and Enceladus, still investigate the complex chemistry of Titan's atmosphere and surface. We just do it through increasingly sophisticated machines rather than by sending fragile human bodies into environments that will kill them. And perhaps that's enough. Perhaps the drive to physically stand on alien worlds, while understandable and even noble, is less important than the knowledge we gain from studying those worlds. Perhaps the real value of space exploration is not in where humans can plant flags, but in how we expand our understanding of the universe and our place within it. There's also a practical argument to be made about priorities and resource allocation. Space exploration, particularly human spaceflight, is extraordinarily expensive. NASA's budget for fiscal year 2024 was approximately $25 billion. That sounds like a lot, and it is, but it represents less than half of 1% of the total US federal budget. For comparison, the United States spends more than that on defense every few weeks. Still, $25 billion could fund a lot of other things: medical research, education, infrastructure, climate change mitigation, poverty reduction. Every dollar spent on sending humans to Mars is a dollar not spent on addressing problems here on Earth. Is the inspirational value of human space exploration worth that trade-off? This is a question without an objective answer. It depends on values, on what we believe is important, on how we weigh present needs against long-term aspirations. Some argue that space exploration drives technological innovation that benefits everyone, that the challenges of operating in space force us to develop solutions that find applications on Earth. There's truth to this. NASA's work has contributed to advances in materials, science, computer technology, water purification, medical devices, and countless other fields. The miniaturization of electronics, driven partly by the need to fit complex systems into spacecraft with strict mass and volume constraints, has benefited every industry. Techniques developed for analyzing data from space telescopes have found applications in medical imaging. Water recycling systems designed for spacecraft have been adapted for use in areas with limited water access. But it's also true that these innovations could have been pursued directly without the intermediate step of space exploration. We don't need to go to Mars to develop better water purification systems or more efficient solar panels. We could invest in those technologies directly, potentially achieving faster progress at lower cost. The counter-argument is that space exploration provides motivation and focus that purely terrestrial research might lack. There's something about working toward a grand goal, about pushing the boundaries of what's possible, that inspires people to excellence and creativity. The Apollo program didn't just land humans on the moon, it mobilized an entire generation of scientists and engineers, created educational programs that trained the workforce of the following decades, and demonstrated that seemingly impossible goals could be achieved through dedication and collaboration. Perhaps space exploration is less about the specific destinations we reach, and more about what the journey reveals about ourselves. The Apollo 8 astronauts orbiting the Moon on Christmas Eve in 1968 took a photograph called Earthrise that showed our planet rising above the lunar horizon, a fragile blue oasis in the black void of space. That image changed how people thought about Earth, contributing to the environmental movement and fostering a sense of global unity. Similarly, the Voyager 1 spacecraft's pale blue dot image, taken from the edge of the solar system in 1990, showed Earth as a tiny speck of light, barely visible against the vastness of space. Carl Sagan's reflection on that image remains one of the most poignant meditations on the human condition. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust suspended in a sunbeam. These perspectives gained from venturing beyond our planet remind us of both our significance and our insignificance. We are the only known intelligence in the universe, the only beings capable of understanding and appreciating the cosmos. That makes us precious, unique, worth preserving. But we're also vanishingly small, confined to one tiny world in an unimaginably vast universe. Our conflicts and divisions, our petty grievances and territorial disputes, seem absurd when viewed from that cosmic perspective. So perhaps one value of pushing to Mars, even if we can't go much further, is the perspective it provides. Standing on Mars and looking back at Earth would give us a new vantage point, a new way of seeing ourselves. It would make concrete what we understand intellectually, that we share one small planet, that our survival depends on working together, that our differences are trivial compared to what unites us. But we need to be honest about what reaching Mars would actually mean. It would not be the beginning of unlimited expansion across the cosmos. It would more likely be the establishment of a permanent outpost, a small community living in enclosed habitats, completely dependent on Earth for support for many decades or centuries. It would be extraordinary and historic, but it would not fundamentally change the human condition in the way that some futurists imagine. We would still be primarily an Earth-based species, with the vast majority of humans living on the planet where we evolved. Mars would be more like Antarctica or the International Space Station, a place where a small number of people live and work, advancing scientific knowledge and testing the limits of human endurance, but not a true second home for humanity in any meaningful sense. And beyond Mars, the solar system would remain largely the domain of our robotic explorers. We might send humans to the moons of Jupiter or Saturn someday, centuries in the future, with technologies we can barely imagine today. But those would be expeditions, not colonization efforts. They would be journeys to the absolute limit of human capability, undertaken by extraordinary individuals willing to risk everything for exploration, not migrations of families and communities seeking new homes. The asteroid belt, that collection of rocky and metallic bodies orbiting between Mars and Jupiter, might be more accessible than the outer planets. Some asteroids pass relatively close to Earth, requiring less energy to reach than Mars. Science fiction often depicts asteroid mining operations and settlements, communities carved into the interiors of rotating asteroids that provide artificial gravity through centrifugal force. This is theoretically possible. The technology required, while advanced, doesn't violate any laws of physics, but the practical challenges are still immense. Asteroids have no atmosphere to slow incoming spacecraft, making landing difficult. They have minimal gravity, making it hard to keep equipment and people anchored to the surface. They're exposed to the full intensity of solar radiation and cosmic rays, with no planetary magnetic field for protection. And they're isolated, far from help if something goes wrong. An asteroid base would be even more dependent on regular supply runs from Earth than a Mars base would be. At least Mars has resources, water ice, atmospheric carbon dioxide that can be converted to fuel and breathable air, regolith that might be used for construction. Most asteroids are just rock and metal, valuable perhaps for their mineral content, but offering little to support human life. So even the asteroid belt, while closer than the outer planets, represents a marginal extension of human reach rather than a major expansion of our presence in space. This brings us back to the fundamental question. If Mars is the boundary, if we cannot realistically venture much beyond it, is space exploration worth the effort and expense? I would argue yes, but for reasons that might be different from the grand visions of science fiction. Space exploration is worth pursuing not because it will let us escape Earth or colonize the galaxy, but because it expands human knowledge, advances technology, inspires achievement, and provides perspective on our place in the cosmos. We should pursue space exploration with clear eyes and realistic expectations, understanding both its potential and its limitations. We should invest in robotic missions that can explore far beyond where humans can safely travel. We should develop the technologies that make space access cheaper and more routine. We should search for life elsewhere in the solar system because finding it would be one of the most profound discoveries in human history. And yes, we should probably send humans to Mars not because it's practical or economically justified, but because some achievements transcend cost-benefit analysis and speak to something fundamental about human nature. But we should also maintain perspective. Space exploration should not come at the expense of addressing urgent problems here on Earth. We should not deceive ourselves into thinking that Mars offers an escape from climate change, resource depletion, or any of the other challenges we face. The only planet we can realistically save is the one we're already on. Earth, for all its problems, is a paradise compared to anywhere else in the solar system. It has breathable air and drinkable water. It has a magnetic field that protects us from radiation. It has a climate that, while changing, still falls within the range that supports human life. It has ecosystems of staggering complexity and beauty, billions of years of evolution producing an interconnected web of life that we're only beginning to understand. Mars has none of this. Mars is a frozen desert with a toxic atmosphere and radiation levels that would kill you. Even if we terraform it over centuries, even if we somehow give it a thicker atmosphere and warmer temperatures, it would still be a pale imitation of Earth, a world bent to our will through enormous effort, but never quite suited to our biology. The outer planets and their moons are even more hostile, beautiful to look at through telescopes, fascinating to study with instruments, but utterly inhospitable to human life without massive technological support. So perhaps the real lesson of space exploration is not that we should leave Earth, but that we should appreciate it. Perhaps the perspective gained from seeing Earth from space, from understanding how rare and precious our planet is, should motivate us to take better care of it rather than looking for alternatives. This doesn't mean abandoning space exploration. It means approaching it with appropriate humility, recognizing that we are part of a larger cosmos, but also bound by its rules. It means celebrating achievements like landing rovers on Mars or flying a helicopter in the thin Martian atmosphere without over-promising about futures that may never arrive. The boundary at Mars, if it exists, is not a failure. It's simply a recognition of reality. Humans are biological organisms that evolved in a very specific environment. We can extend our reach beyond that environment through technology, but only so far. We can survive in space for limited periods. We can probably establish a permanent presence on Mars, but we cannot transform ourselves into beings that thrive in the vacuum of space or the crushing gravity of Jupiter. Some futurists talk about transhumanism, the idea that we might eventually merge with technology, upload our consciousnesses into computers, or genetically engineer ourselves into forms better suited for space. These ideas venture into philosophical and ethical territory far beyond the scope of this discussion, but they also remain firmly speculative. We don't know if consciousness can be uploaded, we don't know what the long-term effects of radical genetic modification would be, and we don't know whether beings so transformed would still be meaningfully human. For now, and for the foreseeable future, we are biological humans, with all the limitations that entails. And those limitations mean that Mars likely represents the practical boundary of human expansion into space. But this boundary is not confining in the way you might think. Even limited to Earth and Mars, even relying on robots to explore further, we still have an entire solar system to study and understand. We have mysteries to unravel about how planets form, how life begins, whether we're alone in the universe. We have technological challenges to overcome in developing sustainable presence beyond Earth. We have philosophical questions to grapple with about what it means to be human in a vast cosmos. And beyond the solar system, we have the entire universe to observe and study. Our telescopes grow ever more powerful, revealing details of distant galaxies, detecting planets orbiting other stars, peering back in time toward the Big Bang itself. The James Webb Space Telescope, launched in December of 2021, is providing images and data of unprecedented quality, showing us the universe in ways we've never seen before. We may never walk on a planet circling another star. The distances are too vast, the energy requirements too enormous, the timescales too long. But we can study those planets from afar, analyze their atmospheres for signs of life, map their surfaces and understand their climates. We can learn whether Earth-like worlds are common or rare, whether life arises readily when conditions permit, whether intelligence and civilization are inevitable products of evolution or astronomically unlikely flukes. These are questions that matter, questions that shape how we understand ourselves and our significance, and we can pursue answers without physically traveling to other star systems. The light that reaches our telescopes carries information about distant worlds, information we're learning to decode and interpret. So the boundary at Mars does not limit our ability to explore or understand the universe. It limits our physical presence, our ability to plant flags and leave footprints, but not our reach in other senses. Perhaps this is the mature perspective on space exploration, recognizing it as part of a larger scientific and philosophical endeavor rather than the beginning of unlimited expansion. We explore space to learn, to grow, to satisfy the curiosity that defines us as a species. We do it knowing that there are limits, that we cannot go everywhere or do everything, but that what we can accomplish is still extraordinary and worthwhile. Mars represents the edge of a particular kind of ambition, the dream of humans living and working throughout the solar system. But it's not the edge of exploration itself, not the limit of what we can learn or discover or achieve. And maybe that's enough. Maybe we don't need to colonize the galaxy to be successful as a species. Maybe we can find meaning and purpose in understanding the universe rather than conquering it, in learning our place within the cosmic order rather than trying to dominate it. This is, admittedly, a less exciting vision than the science fiction futures we've imagined for decades. There are no starship captains exploring strange new worlds, no galactic empires or interstellar commerce. There are just humans doing what we've always done, pushing against the limits of what's possible, learning what we can, and adapting to the realities we discover. But there's a quiet dignity in that vision, a recognition that significance doesn't require cosmic scale, a species that understands the universe, that unlocks the secrets of matter and energy, that creates art and music and literature, that asks deep questions about existence and meaning. That species is remarkable regardless of how many planets it inhabits. The boundary at Mars, then, is both a limitation and an invitation. It limits our physical expansion but invites us to deepen our understanding. It constrains our ambitions in one direction while opening possibilities in others. It forces us to be realistic about what we can achieve while still leaving room for extraordinary accomplishments. In the end, whether Mars truly represents the absolute boundary of human space exploration remains to be seen. Perhaps some breakthrough we can't yet imagine will change the equation, making journeys to the outer solar system or even beyond more feasible. Perhaps fusion propulsion or some other technology will open doors we currently think are closed. Perhaps future generations will look back on our caution and smile at how limited our vision was. But based on what we know now, based on the physics and engineering and biology we understand today, Mars appears to be the practical limit of sustained human presence in space. We might venture beyond it occasionally, we might send expeditions to distant moons or asteroids, but Mars is likely where humanity establishes its first, and possibly only, major outpost beyond Earth. And that's okay, that's still extraordinary. A human standing on Mars, looking up at Earth as a bright star in the alien sky, represents an achievement that would have seemed impossible to our ancestors. It represents the culmination of centuries of scientific progress, the solution of countless technical challenges, the triumph of human ingenuity over the hostile environment of space. If we accomplish that, if we establish a permanent human presence on Mars, we will have demonstrated that we are not forever bound to the surface of our birth planet. We will have proven that human civilization can exist in more than one place, that we can adapt to environments radically different from the one we evolved in, that we have a future beyond Earth, even if that future is more modest than science fiction imagined. And while we work toward that goal, while we push the boundaries of what's possible on Mars, our robotic explorers will continue their work throughout the solar system and beyond. They'll dive into the oceans of Europa, sail through the methane lakes of Titan, sample the geysers of Enceladus, and journey into the space between stars. They'll be our eyes and ears in places we cannot go, our instruments in environments we cannot survive, our legacy reaching forward into a future we cannot predict. The story of space exploration, then, is not really about distance or destinations. It's about what we learn along the way, about ourselves and the universe we inhabit. It's about pushing against limits while acknowledging they exist. It's about dreaming big while staying grounded in reality. It's about recognizing that we are simultaneously the most remarkable thing we know of in the cosmos, and also incredibly small and fragile. Mars may be our boundary, but it's a boundary that still leaves us with an entire solar system to explore, an entire universe to study, and an entire planet to call home and to protect. That's more than enough for any species, more than enough for countless generations of explorers and scientists and dreamers. The real question isn't whether we can go beyond Mars. The real question is what we'll do with the reach we have, how we'll use our capabilities to expand knowledge, inspire wonder, and ensure that humanity thrives not just on Earth or Mars, but across time, carrying forward the light of consciousness and curiosity that makes us unique in the universe as far as we know. So yes, Mars is probably the boundary, but what a boundary it is, and what an achievement it will be to reach it. If you found this exploration of humanity's limits in space fascinating, you'll definitely want to check out the video on the screen. I cover the biological hurdles, the psychological toll, and the realistic timeline for making Mars habitation a reality. See you there.